Assalamualaikum. Now we continue with part number 3 with step number 7, which is to finding the j omega axis crossing. So in this step, we need to find what is our gain and what is our frequency for the system to be stable. Let's recall for the example. Okay, from this example, we need to find the frequency and the gain of k for the which of the root locus cross the imaginary axis. For what range of k is the system stable? So we need to determine the range of k when the system is stable. Okay, by using this transfer function, first step we need to calculate the closed loop of transfer function by using this equation 1 plus gs hs equal to 0. So and then we use the characteristic for the poles number, which is that s equal to 4 plus 7s cubed plus 14s squared plus 8 plus k s plus 3k. Okay, then we need to transform this characteristic equation by using Root-Hurwitz criteria. You can recall for the chapter 3 for the stability analysis. Okay, we start from S4 until S0. Okay, from the Hurwitz table, for the positive k, only S1 row can be all 0. So sini kalau kita ganti 21k equal to 0, k still lagi kita dapat 0 kan. And then we need to determine what is our value of k. So we take it for the row number S1. So by using this to find the value of k, let negative k2 minus 65k plus 720 divided by 19 minus k equal to 0. So we get our k 9.65. Okay, to find the frequency on the j omega axis crossing from the even polynomial by using s squared row with the k equal to 9.65. So bila kita nak dapatkan frequency, we use even polynomial. So this is our even polynomial. Start with 19 minus k s squared plus 21k. So kita dapat persamaan kat sini lah. So we need to replace k equal to 9.65. So bila kita gantikan, kita akan dapat nilai s kita plus minus j 1.59. So as summary, the root locus cross the j omega axis at plus minus j 1.59 at gain of 9.65. The system is stable for k is higher than 0 and k less or equal to 9.65. Okay, the next step is we need to calculate what is our angle of departure from the complex poles or angle of arrival to the complex of 0. So to determine the angle of departure, we have 118 degree minus net angle from the all poles to the poles plus net angle from 0 to the poles, while angle of arrival we have 180 degree minus net angle from the all 0 to that 0 plus net angle from poles to that 0. Okay, this is example. From the figure, the departure angle is 180 degree minus theta 4. This is our theta 4 plus theta 5 plus theta 2 plus theta 3 plus theta 6. Kita tengok kat sini theta 4 plus theta 5. This is our theta 4 and this is our theta 5. So theta 4, theta 5 dia kata net angle from all poles to that poles. This is our poles, poles to poles, and poles to poles. And then net angle from 0 to that poles. 0 kita kat sini, 0, 0, and also 0. 0 to poles, and 0 to poles, 0 to that poles. Okay. The next is, we need to calculate our angle of arrival. Angle of arrival is at 118 degree minus net angle from other 0 to that 0, and plus net angle from poles to that 0. So we have 100 degree minus theta 3 plus theta 6. What is our theta 3? Theta 3, this is our theta 3, 0 to 0, and then 0, 6, 0 to 0. Okay, net angle from poles to that 0. So poles to 0. So here we have poles to 0, poles to 0, and poles to 0. So we have theta 1 plus theta 4 plus theta 5. Okay, the last, we need to calculate the value of K on the root locus. The value of K is at arbitrary point S1 in the root locus is given by. So to calculate the value of K on the root locus, you just use this equation as a given. Okay, we continue with extra example on the next part. Thank you.